the first and second derivatives of the following cubic function and show that there are two turning points, and that the maximum is at minus 5/3 and the minimum is at x equals 3, and sketch it. Right, first derivative, that's not much bother anyway, right? So just switch to black here. That's y equals that there. Well, the first derivative is dy dx. dy dx equals, well, you see this wee 3 here, it comes down and it multiplies by whatever's sitting in front of the x, which is a 1, right? 3 ones are 3, so that's 3x, and the 3 reduces by 1 to a 2. And then we do the same thing here. This 2 comes down, multiplies by the minus 2, and gives us minus 4x, and the 2, take away 1 from the 2, we get a 1. And we normally don't write in the 1, so we can scrub it out, or leave it there, but normally it's scrubbed out, okay? We just know it's there. And so on, right? Minus 15x. Well, you see here, there is an actual 1 up there. The 1 comes down, multiplies by the minus 15. The x remains there, but the 1 reduces by 1. 1 minus 1 is 0. And anything to the power 0 is 1. And that includes x to the power 0 is 1. So that becomes a 1. 15 times 1 means that it's just effectively minus 15. And eventually, and then this guy here, minus 12, when you differentiate a constant, you get 0. So this is the first derivative. Now it can also be written down with this type of notation, f dash of x, right? So whether you use dy dx or f dash of x doesn't matter. So what are we looking for next? We're looking for the second derivative, right? So that's the first derivative differentiated again, the 2y dx squared, and that's also can be written as f double dash of x. Okay, so in this case we're differentiating the first derivative. 2 times 3 is 6, 6x. 2 minus 1 is 1, so we'll just leave our 1 here, our invisible 1. And again, 1 times minus 4 is minus 4 times x to the power 0 disappears, and the constant disappears completely. So this is our second derivative, 6x minus 4. And now we want to show that there are two turning points. Well, the turning points occur when the first derivative is also gives us the slope, right? It's well tied up with the slope. So when the slope is 0, you know, like our curve is going to have 2 turns because the biggest has up to 2 turns because the biggest power of x is 3. So there's going to be a maximum of 2 turns on our curve, right? That's just any old curve I've sketched there, and that there would be the max, and that would be the min. And at the max and the min, the slope is 0. You're neither going up the hill or down the hill. The slope is 0. The slope of a tangent to the curve at those points is 0. So dy dx is 0 at those points. dy dx is 0. So we know that dy dx equals 3x squared minus 4x minus 15. So if we set this equal to 0 and solve it, we'll get values of x that correspond with our turning points. So how are we going to solve this? Let's see there now. 3 times minus 15 gives us minus 45. 3 times minus 15 equals minus 45. We're going to split this 4x here in the middle somehow or another. Minus 45. It's like 9 5s, isn't it? 9 times 5 minus 9 times positive 5 gives us minus 45. So let's try that. 3x squared minus 9x plus 5x minus 15 equals 0. Right? So this here evaluates to minus 4x. We haven't really changed it. We've just rearranged it to suit our own purposes here. So we can factor out 3x out of the first two terms. So 3x times x minus 3. And you see with a similar pattern here, we're going to factor out 5 out of the next two terms. We have x minus 3 equals 0. So I can rewrite this as 3x plus 5 times x minus 3 equals 0. So this here is just the top line rearranged to suit our purposes. Now I'm going to make some space, rub out this stuff. And you see we've two items multiplied by each other equals 0. So each of those could be 0. So if 3x plus 5 equals 0, or x minus 3 equals 0. And this gives us here, if we take away 5 from both sides, we end up with 3x equals minus 5. And then we divide both sides by 3. We have x equals minus 5 over 3, and on the other side our x equals 3. So these guys marked in blue here, these are the values of x at the turning points of our function. Right? So we've now shown that there are two turning points. So we have our first and second derivatives. We've shown that there are two turning points, but now we need to show that the turning point at x equals minus 5 over 3, we have to show that that turning point is a max, and then show the other one is a min. Right? And how are we going to do that? Well, we'll make some space here first. And I'm going to rub out this stuff. So to determine the nature of the turning points, we use the second derivative. Right? So, where's our second derivative? This is our second derivative here, 6x minus 4. So, we run this point here, we run this x value through it. So we have 6 times minus 5 over 3 minus 4. And we want to know if this here is going to be bigger, greater than or less than 0. Now it's going to be less than straight away without actually working it out, because this is 6 times a minus number minus a 4, so it's all going to be minus. So this here evaluates to being less than 0, right? And because the second derivative using this value of x is less than 0, this means that the turning point at x equals minus 5 over 3 is a local max. Right? And we can do the same with our other point, our other x value equals 3. So running that through 6x minus 4, 6 times 3 minus 4, 6 3s are 18, minus 4 equals 14. And that's a lot bigger than 0. And that indicates that the turning point at x equals 3 is a local minimum. Right? So we've shown now that the maximum is at x equals minus 3 and that the minimum is at x equals 3. Finally, we just want to sketch our curve. Right? Now, looking at our curve again, this is it, our curve, y equals all this mess here. When x is 0, the first 3 terms will be gone. You see that? 0, 0, 0. So y will equal 12 when x is 0. Y will equal minus 12 when x is 0. So there's another point on our curve. Right? It's called the y-intercept. So to draw this, we don't need a work of art, right? Here's our y-axis. Here's our x-axis. Our local min, or our graph is going to cross at 0, minus 12, somewhere down here, right? We can call that 0, minus 12. Our local max will occur at x minus 1 and 2/3, right? Our local max will occur there somewhere. Our local min will occur at x equals 3. So that'll be a local min. So that's going to be below this guy, I suppose. Down here somewhere. Oh yeah, and to find out then what the y, see, we don't need the y, we don't have the y coordinates. That's going to be 3 something, right? This one here is going to be minus 5 over 3 comma something. To find out the somethings, we need to run those values through the original curve. Right, so clear this off. Okay, so to find out the y value, say when x equals 3, when x equals 3, y will equal 3 cubed minus 2 times 3 squared minus 15 times 3 minus 12. That'll be our y value. What'll that be? With the calculator, 3 to the power of 3 minus 2. Delete that there now. Something gone wrong, right? Minus 2 multiplied by 3 squared is 9. Minus 45 minus 12. And I get minus 48 there. Minus 48, right? So we're going to have a minus 48 here. The very depth of the valley this guy goes to is minus 48. So we might need to readjust our sketch. But we're just getting our 3 points in order first anyway. 3 minus 48. And when x is minus 5 over 3, y will equal minus 5 over 3 cubed minus 2 times 5 over 3 squared minus 15 times 5 over 3 minus 12. So it'll come to 2.815. So that point there is minus 5 over 3 comma 2.815. Right, so our graph is going to have high mountain here, our max, and it's going to have a really deep min down here, something like this, right? Down here, the local min will be 3 minus 48, and the local max, that point there, will be minus 5 over 3, comma 2.815. Now you could do a better job of this yourselves. And then the y-intercept is going to be 0 minus 12. Right? 0 minus 12. And that's it sketched. And I have it done on Desmos. I'm going to show you that there now. Right? That's it there on Desmos. There's the local min. There's the local max. And there is the y-intercept. That's it.